All right, so welcome back. So we are still in Chapter 5, Section 7, and hopefully this should be the last video of this chapter. And so, again, we are integrating trigonometric functions. And if you don't mind, let's fast forward a little bit, right? So let's assume that a question like this is, say, staring at you on some test, right? And obviously, so you want to be able to integrate it. One of the problems for younger calc students, young math students, is they have a whole lot of tools, right? A whole lot of tools that they have learned, but the order in which to use them, or knowing when to use which tool, takes a little bit of time, right? Takes some time. So, but nevertheless, so you're staring at this. We want to integrate, right? And maybe you're thinking, you're thinking to yourself, well, wait, can I use substitution? So you start going through a whole lot of different techniques. And here is a technique that you might forget about, you might forget that you even have access, that you are even allowed to do such a technique. The idea is, can we rewrite this integrand before we start trying to integrate it? Is there a way to rewrite it? Well, look, if I have a plus b over c, you know that I can write that as a over c plus b over c, right? And maybe it just so happens that we should break up this integrand from one fraction. We should break it up into two fractions. And let's see if that sparks any ideas of how to integrate this guy, right? So we can break this up as x over the square root of 4 minus x squared dx plus the integral of 2 over the square root of 4 minus x squared dx. And now we can try to figure out which integration technique would work on each. So first off, this is something out of Calc 1, right? You can just simply use U substitution when integrating this. This is not a arc sine, arc tangent, arc secant problem. However, this is, right? Now, so again, things that I've seen my students confuse themselves on. So if you don't mind, let me pretend that I'm a Calc 2 student. So I'm thinking to myself, well, wait a minute, this guy kind of looks like one of the integration functions for trig, or integration formulas for trig functions, but but they all involve having a 1 in the numerator, where we have a 2, right? So like this is 1 du, 1. So, well, again, I can take a constant. I can always pull a constant out in front of the integral. And of course, I can bring my dx up here so that it matches your formulas exactly. But these are the little things that can escape us, especially under the stresses of taking a test. Now, so I've already done we've done questions harder than this, and I'm not going to, in a video, go back and go through Calc 1 exercises. But just for your sake, that I went ahead and published the solution to and unpacked it for example 3, so that hopefully you can say pause the video, take a screenshot, whatever is convenient for you, and my hopes is that you can work through that integration and make sense. Now, the next little technique that we need before leaving chapter 5 is how completing the square can also help us with integration. Let me, if you don't mind, let me back up for just a second, and I'll just go ahead and tell you what we're going to do. So we're going to use completing the square to make our integrands look like those in the formulas. That's the goal. Let's start with what the heck do we mean by completing the square? Well, how about before I talk about that, let's go back to what if I were to ask you to factor this trinomial? Well, that's not bad. I think you can probably do that by inspection, right? So this would be x plus 2. This would be x plus 2, and we can rewrite that as x plus 2 squared. Now, this is what we call a perfect square trinomial, right? What we're going to do is we're going to use completing the square techniques to help us write these trinomials as perfect square trinomials. And then they're going to be able to fit like a puzzle piece into those integration formulas. So just notice something. All I want to do is I want to draw attention to this 4 before I do anything else. Notice that when you're looking at at any quadratic, all right, any quadratic can be written as ax squared plus bx plus c. Of course, the a cannot be 0, but the a, the b, and the c, these are just constants, they're coefficients. And I want to, let's go ahead and let you and I agree that a, in this following example, would be 1, and I think you and I agree that b would be 4 and c would be 4. But that's not really what that's important right now. What I want to draw attention to is this 4. And I want you to see how I could build that 4 by taking b, cutting it in half, and squaring it. Let's see if that works. So you and I agree that b is equal to 4. And if we cut 4 in half and square it, that's just 2 squared, and 2 squared is 4. And so notice that this matches. Now, what if I tried that technique here? Well, obviously that's not going to work, right? If you take b, cut it in half, and square it, I am not going to get 5. Right, so b, we cut b in half and then square it. So that would be, as we saw above, 4 over 2 squared. So this is supposed to be 4. So what does that mean for this trinomial? So that means that this is not a perfect square trinomial. I can't write it like this. But let me see if you can follow me here. What if I were to bring this 5 to the right side of the equation? Okay, so far so good. And now I want this quadratic to look like a perfect square trinomial. So don't you agree with me that I would need to have a 4 here in order to factor it to make it look like this, right? I would need to plus 4 on the left side. Well, I can plus 4 on the left side of that equation as long as I'm willing to add 4 on the right side of that equation. So what does that look like? Well, that's just going to be, let's add 4 to this side, and we counteract that by adding 4 to this side. So let's see what that looks like. So now it's x squared plus 4x plus 4 is equal to -1. And now, just as we saw up here, I can factor that to be x plus 2 squared is equal to -1. Okay, so with this technique in mind, let me see if I can show you how you can use this technique here to your advantage when integrating. By the way, just as an aside, if you've ever, you know the quadratic formula, right? So if you know the quadratic formula, that you've all have used it before. By the way, if you take this formula here, ax squared plus bx plus c equals 0, and you complete the square, you know what you'll get? You will get the quadratic formula. There you go. Just keep that in your pocket for some trivia next time you're, I don't know, at the bar or something. You want to show off. Ready? Let's see if we can use this completing the square technique. So, all right, here we go. So we want to integrate the following. I'll be honest with you, I normally don't write my integrals like this. I would write that integral as x squared minus 4x plus 7. I don't normally keep my dx in the numerator, right? I like to keep my dx off to the right. So in my mind, I look at it like this. I'd write it like this. But it's the same thing, okay? You can just imagine that dx imagine the dx over 1, if that helps you. So, and that's why you can write that dx in the numerator. Okay, so listen, right now, you do not have a way of integrating this. Right, there is no formula that you have been given access to thus far that could help you in this integration. No u substitution, no nothing works at this stage. You also take a look at this. You can't break up the fraction like we did in the previous problem. That's not going to work either. So you're kind of stuck. So what can you do? Well, let's see if we can rewrite this trinomial. Let's see if we can complete the square, and I'll show you why. So let's switch it up a little bit. Ready? So you got x squared minus 4x plus 7. That's the denominator in our integrand. Now, remember on the previous page, well, actually, my apologies. Let me see if I can give myself a little bit of space before I keep chatting. I'll come back to that in the previous page. Give me just a second. So, first off, is this a perfect square trinomial? Well, remember, it's take b, cut it in half, square it. So in our case, right, b is equal to -4. So if I take -4 and I cut that in half and then I square it, the real question is, do I get 7? Because if I do, then I have a perfect square trinomial. Well, what do I get? Well, let's figure it out. So -4 divided by 2 is -2 squared, and -2 squared is equal to 4. All right, so this is not a perfect square trinomial, right? Because I have a 7 here. I would need to have a 4. Now, let me get back to that comment on the previous page. Do you remember how at this stage, right? Remember I took the 5 and brought it over to the other side. And do you remember how I added 4 on one side of the equation and added 4 on the other side of the equation, right? Well, I can't do that here. I don't have an equation, right? There's no equal symbol. I'm trying to evaluate an integral. But let's see if you can follow me here. So what I can do is this. I want to have a 4 here so that I can factor this. So I want to have x squared minus 4x plus 4. Right, I want to be able to add a 4 here so that this will become a factor to be a perfect square trinomial. But I can't just add 4 inside my integrand unless I'm also willing to subtract 4 at the same time. Stay with me. If I take your age and add 4 years to it, while at the same time subtracting 4 years from it, I haven't changed your age. Agreed? So if I add 4 here while also subtracting 4 here, everything is okay, right? So let's write that complicated looking integral. So now I'll go ahead and put my dx out here like I did above. So now I have all of this going on. Right? So at first you're like, wait a minute, my integrand, it appears to be getting more and more complicated. But it's actually not. So we now can write, let's go ahead and take this whole trinomial, and we can write that as, that would factor to be, what? It would factor to be x plus 2. Actually, I think I said plus 2. That should be minus 2. So x minus 2 squared. And let's also combine here. 7 minus 4 is 3. So plus 3. So now let's take this and write it here. Right, so x minus 2 squared plus 3. Wait a minute. That looks like some of the formulas that we were using in the in the previous page. That looks like one of those arcsine, tan, secant formulas, and it is. And this, and hopefully you can spot that's actually arctangent right here. This is an arctangent formula. Well, if it's an arctangent formula, then let's start with the constant. A squared is the 3. Let's go to the function. So u squared, well, u squared is x minus 2 squared. So now let's use this information to figure out what, if a squared is 3, what is a? And if u squared is x minus 2 squared, what is u? Well, that's easy enough. We can figure that. So if you square something to get 3, that must have been the square root of 3, right? The square root of 3 squared is 3. And if you square something to get x minus 2 squared, you must have squared x minus 2. All right? So far so good. We now can sub an a squared here. We can sub a u squared here, but you still got to deal with this dx. So let's see what that, so if u is x minus 2, then what is du? Well, the derivative of u with respect to x would just be 1, right? The derivative of x is 1. The derivative of negative 2 is 0. So that would be 1 dx. Or in other words, du is equal to dx. That's one of the best case scenarios, where now if du equals dx, then wherever I see a dx, I can simply substitute du. Now it's perfect. So now, if I substituted everything, it would look exactly like the setup for arctan. U squared plus a squared. Okay, and that means I can jump right to the answer they give us, which is 1 over a arctan u over a plus c. And the only thing left to do is plug in. So I need to put the square root of 3 in for the a. I need to put the x minus 2 in for the u. All done. So 1 over the square root of 3 arctan x minus 2 over the square root of 3 plus c. Okay. Last couple things I want to say about the completing the square. Sometimes you run into scenarios that look something like this, and you still might need to complete the square in order to integrate. So let's see if we can notice the difference between what we're looking at now and the ones previous. Well, for the first example, notice that we now have a 2 as a coefficient in front of the x squared. So in cases like that, you want to be able to factor out whatever coefficient you want. In other words, you want a 1 attached to your x squared before you go through and start completing the square. So in this case, we can just factor out a 2, leaving us with x squared minus 4x plus 5. Okay, and now you can complete the square from here. So for the next example, well, first off, let's make sure we write this in order, right? So this should be written in descending powers, so negative x squared plus 3x. That's the first thing to notice. Next thing to notice is that we now have a negative in front of our x squared variable, so let's factor out a negative, so that we have x squared minus 3x. And now you can complete the square here. This is actually nice because I'll go ahead and do that. So remember, if you want to complete the square, it's b, take b, cut it in half, square it. So in this case, our b would be equal to negative 3. So this would be negative 3. We would cut that in half, and then we would square it. So what is that? Well, if you square negative 3, you have 9. If you square 2, you have 4. So this becomes what you want to add or subtract so that you can complete the square. Now, we've already done all the work for the next and final example. So let me take this along for the ride here. So notice that you are, so in this particular case, let's start with the integration. I'll get to the question in just a second. So if we want to be able to integrate 1 over the square root of 3x minus x squared, doesn't match any formulas that you have access to right now, but what you decide to do, take a look here, you decide to rearrange that, subtract out a negative, And now you know that if you add 9/4, you can write that as a perfect square trinomial. So let's go ahead and set that up. So we got 3x. Let's go ahead and let me write it this way. My apologies. So 1 over the square root of 3x minus x squared. We want to rewrite that. We want to rewrite that as, well, we want to have negative x squared minus 3x. Let me go ahead and write that here. And now, what we want to be able to do is add 9/4 here, and we can do that as long as we're also willing to subtract 9/4 here. All right, so if that's the case, then our integral looks like this. So 1 over, don't forget about your negative symbol, x squared minus 3x. Here's our plus 9/4 minus 9/4. dx. All right. So what does this guy factor to be? So now it looks like this. Go ahead and put my square root symbol in here. So now let's go ahead and factor. Let's see what that looks like. So that would factor to be 9/4 minus x minus 3/2 squared. All right, and now our integration formulas can help. So here, this is a squared, this is u squared, and it all should you should be able to finish it from there. I'm going to go ahead and provide. Well, actually, let me actually read the question, because in this particular question, they're asking you to find the area of the region bounded by the graph of the following function and the following vertical lines. So I'm going to flip a page real quick. Let's see if I have that graph anywhere. I do not. So if you were to draw that out, you're gonna have a few vertical lines, and then you're gonna have a function, and you're trying to find the area bounded between all of those lines and graphs. And so really what you have here is, if you're trying to find area, you're using definite integration, not indefinite, right? So we would be going from 3/2 to 9/4. So let me go ahead and get you to the answer. I know this is, this is a long section, and there's not very many applications, so it's not very exciting either. So x minus 3/2 over 3/2, and we still need to back substitute from 3/2 to 9/4. So all of that gets us to arc sine of 1/2 minus arc sine of 0, which is equal to pi over 6. That's the area bounded between all of that. Okay, so from here we're going to go, this will be the end of chapter 5. We will not be studying chapter 6, so we will be skipping that section, or that whole chapter, which deals with differential equations. It's just an introductory, elementary overview of differential equations. If you have to take differential equations, you maybe decide to take it with me, maybe not. Either way, you will get, that's, in that course is obviously where we'll study that chapter and more. But we will be going to chapter 7 next, and chapter 7 is where we start to see some applications of these integration techniques. Okay, so I will see you there.